Hey guys, welcome to Safi Mixed. In this video, I'm going to prove a very important trigonometric relation called reduction formula. It has a lot of application in solving simple harmonic oscillators, whether that is a bob connected to a thread or a mass connected to a spring, or in other words, that harmonic oscillation is being executed by an electrical capacitative circuit. In all these cases, this reduction formula has a key role. And the parameters A and B then represents the initial conditions of the solution to differential equation of harmonic oscillator, and theta represent the phase, and X is a time-dependent dimensional parameter which represents the instantaneous values of the solution to the differential of harmonic oscillator. Equation 1 can be proven by solving the second order differential equation for harmonic oscillator with initial conditions A and B. However, here I want to prove this through a geometrical representation of right angle triangle. To this end, consider a right angle triangle of this form where the vertices I represent with A, B, and C, and the side lengths AC and AB I respectively represents with A and B. Now, using Pythagorean theorem, the length of side BC, which constitutes the diagonal of this triangle, equals square root of A squared plus B squared. Next, I represent the angle at what is B with theta. Now, with theta given at vertex B, the side AB then becomes the base of this triangle AC, perpendicular, and BC obviously is the hypotenuse. Now, using the definition of cos and sine function, cos function is equal to base by hypotenuse. Therefore, I can write cos theta equals b divided by value of hypotenuse. And similarly, the sine theta can be expressed as perpendicular by hypotenuse, and I can write this equation like this. Now, consider this function sine of x plus theta, and we use the trigonometric relation of sine a plus b to write sine x plus theta equals sine of x cos of theta plus cos of x sine of theta. And if I use the values of cos of theta and sine of theta from equation 2 and 3, I can put the result of the right side of this equation into this form, where I have substituted b divided by a squared plus b squared for cos theta, and similarly I can write the value of sine theta at this position. Now the two terms carry the same denominator, therefore I can take this common and can put the right side of this equation into this form. B sine x, this b multiplied with sine x would make it b sine x, and this a multiplied with cos of x would make it a cos x. And now if I take the denominator to the left side of the equation, I can rewrite this equation into this form. Now if you look carefully, the right side of equation 4, that is b sine x plus a cos x, is in fact the left side of equation 1. B sine x at this position and a cos x at this position. And similarly, the left side of equation 4 is in fact the right side of equation 1. That means we have proven this identity. But wait, there is one parameter missing from our geometry, and that in fact is the parameter x in equation 1 or in equation 4. So now how can we link this parameter and the geometry of this triangle and in this equation? So that we can do very easily. Let me define the angle at vertex C inside this triangle by x. So when we know about the angle at the vertex x and we want to solve this triangle, then the side AC makes the base and side AB is the perpendicular of triangle. So in terms of angle x at vertex C, the cos function and the sine function are now defined as cos x is equal to a divided by a squared plus b squared, because now the base of this triangle is a. And similarly, the sine of x is given by b divided by hypotenuse, because the perpendicular of this triangle is now side AB, which is equal to b. If I substitute these values in the right side of equation 4, I can write equation 4 like this. B at its own position, and I'm putting the value of sine of x, which is b divided by hypotenuse, and similarly a at its own position and putting the value of cos of x, which is a divided by hypotenuse. So now b times b is b squared and a times a is a squared, and both terms carry the same denominator, so I can simplify this into b squared plus a squared, and I can cancel the square root in the denominator to put a square root over the numerator, and can reduce this into a squared plus b squared. Yeah, this is amazing. In fact, a squared plus b squared is the hypotenuse. This means each side in equation A in fact represents the hypotenuse of the triangle. And in the case of simple harmonic oscillator, each side is in fact the instantaneous displacement from the origin of the equilibrium position. Thanks for watching.